When a customer taps a card at a checkout counter, the payment terminal waits for an answer. In that brief window, the system behind the scenes must definitively prove the buyer's identity before the physical hardware times out. We are operating on a strict mathematical boundary, a 50 millisecond P99 latency budget. That is the maximum allowable time to ingest the data, evaluate the risk, and return a final decision. Attempting to query historical spending habits from a traditional relational database during this window will immediately blow that budget. Traditional disk-backed queries are simply too slow for real-time authorization. Maintaining a capacity of 100,000 transactions per second requires abandoning standard architectures in favor of a specialized real-time machine learning pipeline. The process begins when the API gateway receives the raw transaction payload from the merchant. To prevent a massive bottleneck, the gateway immediately offloads this payload into an event stream, typically Apache Kafka. A stream processor like Apache Flink then attaches. It maintains real-time windowed aggregates, such as a 60-second velocity counter tracking how often a card is used. Batch processing fails here because it cannot provide real-time context. By the time a batch job flags a pattern of suspicious activity, the transaction window has already closed. By decoupling ingestion from processing via streaming, the system can absorb massive traffic bursts without degrading evaluation speed. To bridge data and inference, we use a feature store, split into a bulk offline store and a low-latency online store. The stream processor writes velocity counters here. The gateway merges this historical data with new payloads, forming an enriched feature vector. If the system relies on multiple unsynchronized caches, it triggers a coherence break. This happens when different parts of the pipeline read conflicting data, leading to inconsistent and inaccurate fraud scores. Forcing every component to pull from a single synchronized online store ensures that every model bases its decision on the exact same microsecond of truth. Linear evaluation is too slow. The enriched feature vector is evaluated by two distinct systems simultaneously. The top path is the deterministic rules engine, executing hard blocks on simple logic. The bottom path is the ML inference engine, identifying subtle behavioral patterns rules might miss. These models are specifically compiled for edge inference, using frameworks like ONX runtime, ensuring the complex math executes in under a millisecond. Both paths feed back into a centralized decision block that issues the final verdict: approve, deny, or trigger a 3D secure step-up. This dual-path approach ensures regulatory rules are enforced instantly, while complex behavioral risks are evaluated right alongside them. Managing a distributed system at this scale requires deep observability. Telemetry tools like OpenTelemetry allow us to monitor CPU load and latency spikes in real time. If a network partition or heavy traffic load causes the ML engine to stall past 15 milliseconds, the system faces a critical choice. We resolve this with a fail-open circuit breaker, routing the transaction around the stalled engine directly to an approval. From a business perspective, it is safer to approve the transaction and flag it for asynchronous review than it is to let the payment terminal time out and lose the sale. Robust architectures prioritize graceful degradation under pressure, ensuring that infrastructure failures never leave a legitimate customer stranded at the checkout. This completed architectural blueprint is a unified flow from the API gateway through event streams and feature stores into the parallel scoring engine. A single transaction can now move through every component and output a decision while staying within the 50 millisecond limit. The combination of streaming ingestion, centralized in-memory state, and fail-open inference is what unlocks the capacity for 100,000 transactions per second. In the high-stakes environment of fraud detection, even the most accurate machine learning models are useless if the underlying architectural plumbing isn't designed to deliver them in milliseconds.